One is on Wednesday, September 4th, right? It's on the sections 1.3, 2.1, 2.2, 2.3, web work, homework 1, homework 2, lecture notes and worksheets of the same section, okay? Now there are going to be 5 questions on the quiz. One of them is like, is the differential equation linear or non-linear? The second one is a function a solution of differential equation or not? The third one is solve the initial value problem using variable separable method. The fourth one is solve the initial value problem using method of integrating factors. The fifth one is an application problem. Now the application could be I think I did few, 2 or 3, a circuit problem, or it could be a tank problem, or it could be a Newton's law of cooling, or it could be a population problem, okay? Now, what is the best way to prepare for the quiz? Study the worksheets, study the web work, study the lecture notes, study my past assessments. Now, the demands have been increasing, meaning first I posted my assessment, then someone wanted blank assessment, so I posted my blank assessment. Someone emailed me, 1 semester is not enough, could you add more? So I added spring. Okay, now why did I not add 1 more? Why only 2? I will add the third one as the time goes by. I mean, I have to pull out stuff, right? Just to get started, I did that. So I'll do that, but that's the way you should study. Worksheets, web work, past assessments, lecture notes, and if you still have time and if you still want to master, go for the exercise problems. It's really interesting when you open the textbook and read it. It's really nice. Okay, read it. That's about that. And now, when you say you did web work, please make sure that you really did web work, because last time I gave a problem from web work and 50% of the people didn't solve it. But on web work, it had 100%, everybody did it correctly. So I thought you aced it. So I thought I was playing to your strengths, but I found out otherwise. Okay, don't do that. Don't do that to me. Meaning I won't know how to read it then, right? So web work, no inside out, worksheets inside out, lecture notes inside out, assessments inside out. Don't look at the assessments and try to predict what problem is he going to give. Don't do that. Okay. The problems are very straightforward. If you are able to do worksheet problem, web work problem, lecture notes problem, you should, in the past assessment, you should be able to do it without any problem at all. I mean, it should be easy and nice. I played it really straight, nothing complex. I want to add that there could be a U substitution inside the variable separable. There could be an integration by parts in method of integrating factors. So you should know them. I'm not going to ask you trig substitution. I'm not going to ask you partial fraction decomposition. So those 2 are off the table for now. Okay. So, but U substitution and integration by part very much on the table. Is that clear? If you look at the past assessment, they do have it. So you will see them. Okay? All good? Any questions? Okay. That's about the quiz. And the next thing is about the lecture. So we're going to discuss about the difference between linear and non-linear problems today. So what have we done so far? We have been studying only first order differential equations, right? What is the order? What is an ordinary differential equation? What is linear? What is non-linear? What is autonomous, non-autonomous? Then we studied qualitative analysis. In other words, what is the critical point? What is the critical point? Is the critical point stable, unstable, or semi-stable? Asymptotically stable, semi-stable, or unstable. Then after that, we wanted to solve first order initial value problems using variable separable, first order initial value problems using method of integrating factors. Now, variable separable was able to solve both linear and nonlinear problems, and when we solved using variable separable, we got some solutions to be implicit, some solutions are in explicit form. Okay, but when we solved linear problems using method of integrating factors, we always got explicit solution. That's what was our observations, and then we did applications in the last lecture. Okay, clear? Now today is a slightly theoretical part of it. So I mean, you ideally want to do this. You look at a first order initial value problem. You want to look at it and you want to be able to say, does there exist a solution? If so, where? Like on what domain does the solution exist? Is that the only solution, or are there more? Once you get this, you want to go about finding the solution. Are you with me on that? You don't want to spend about a few years solving the problem and then discover that there does not exist a solution for this problem. You don't want to do that. So first thing is you always want to know, okay, does the solution exist? Where does the solution exist? Is that the only solution? All that, and then you want to go about solving it. But I'm teaching you the other way around. I mean, why? Because the existence theory is little theoretical in nature. I didn't want to start the semester on a theoretical note, so I just picked out the computational route and then I'm coming back to it. Okay? So some textbooks would refer to it as existence theory. Some textbooks would refer to it as difference. Our textbook refers to it as difference between linear and nonlinear equations. Okay? So now first we will discuss about the linear case. I mean, first we want to discuss about the linear first order initial value problem. So we are talking about a problem like y prime plus p of t times y equals q of t, and your initial value is y at t naught is y naught. Okay? So y at t naught is y naught, right? And then now coefficient of y prime is 1, p of t is the coefficient of y, q of t is the right side. You want to find the integrating factor. Integrating factor is e to the integral p of t dt. Then you would write derivative of integrating factor times the dependent variable is integrating factor times the right hand side. You would integrate both sides with respect to t, find the explicit solution. Is that clear? Yes? You know the procedure, you have done it, you have done it in the method of integrating factor and also in several applications, so you know the route. So how does that translate it? I mean, let's pick a problem like this. We had a problem like ty prime plus 2y plus 4t squared. So we said, okay, make the coefficient of, step 1 was make the coefficient of y prime equals 1. Then we got y prime plus 2 over t times y equals 4t. My initial value is y of 1 equals 2. Then step 2 was, okay, my p of t is 2 over t, right? And my q of t is 4t. And p of t is, where is p of t continuous, or where is 2 over 2 continuous? Anywhere but 0. So t is not equal to 0. P of t is continuous everywhere except t equals 0. Okay, so thank you, very nice. Is continuous everywhere except t equals 0, right? Everywhere except t equals 0, right? Where is q of t continuous? Is continuous is everywhere, right? Is continuous, very good. Is continuous everywhere, right? Now the smallest interval, is continuous everywhere except t equals 0 means you write negative infinity to 0 union 0 to infinity. This one is negative infinity to positive infinity. Do you agree with me on that? Now the smallest interval where the p and q are continuous and containing the initial value, this contains the initial value t equals 1. So you would write, so the interval of existence is the smallest interval where the function p and q are continuous. n contains the initial value, and contains the initial value. Initial value y of 1 is 2 and contains the initial value. Let's write it that way. Value is, in this scenario, 0 to infinity. Do you agree with me on that? So the interval of existence is 0 to infinity. Okay, so the t equals 1 lies here, so the smallest interval where your function p of t and q of t are continuous and containing the initial value is 0 to infinity, so the interval of existence is 0 to infinity, and that's why when we graphed it we got this one. Is that clear? And we use variable separable method and we got our solution to be y equals t squared plus 1 over t squared. Does that make sense? Yes.
Why is it 0 to infinity? Because the curve isn't continuous at t is equals to 0.
That's why it's open interval. 0 is not contained in it. Are you all okay with that? Yes.
So basically you split the function to the p of t and q of t parts, right? So what does this like indicate? Like what does this mean? Like if it's continuous, like if p of t and q of t are continuous, like at separate points, what does that actually mean?
What does that mean? Okay, that means now in the context of this problem, it means that my differential equation is well defined, or my solution is continuous on only, not everywhere, only on the interval 0 to infinity, because that's where the problem is well defined.
Because the
If you-
value that's given is t.
If you put, like, my problem is ty prime plus, I think 2y equals 4t squared, right? Now if you put I will get 3 cases. Now when my t is negative, okay, then I would get certain solution. Do you agree with me on that? In other words, my solution would look like this. Okay, rough sketch. When my t is positive, I get ty prime plus 2y equals 4t squared. So then my solution would look like this. Okay. When t equals 0, I do not have a differential equation. I get 2y equals 2y equals 0, so y equals 0. I don't have a differential equation. You see that? So that's what that. So when I'm saying, if I'm picking, but my initial value, this one has y of 1 equals 2. So I'm telling I want a solution for the differential equation passing through y of 1 equals 2. Then in that scenario, this is my solution. So the p of t in the intervals of continuity is pretty much telling me, okay, if my initial value is with 1 and 2, I should go with that interval, not the other one. Make sense?
Yeah.
Now I don't remember which this class or this class, but the previous class, I had a question: y prime plus 2 over t times y equals 4t, and what happens if my initial value was y of 1 equals 2? I think I had a question like that. I don't know if it is your class or the previous class, but that was from that section somewhere. I don't know who it was. But I mean, the solution turned out to be t squared plus 1 over t squared still. Are you with me on that? But, your p of t is continuous everywhere from negative infinity to 0, union 0 to infinity. And your q of t is continuous everywhere, negative infinity to positive infinity. Recognize your p of t is going to be 2 over t and q of t is 4t. Now the initial value y of negative 1 equals 2 is pretty much in this interval, not from 0 to infinity. It is in the interval negative infinity to 0. Is that clear? So the interval of existence would be negative infinity to 0. So the interval of existence is the smallest interval where P of t and Q of t is continuous and the initial value is contained. So it's pretty much, it's very vastly influenced by the initial prescription of the initial value. Is that clear? So if I were to guess it, I mean, my solution, this is a guess, my solution would look like this. The only reason is I'm thinking solution y is an even function. So if it's an even function, it should be symmetric about y-axis. So I just drew it the other way around. Are you with me on that? So, yes.
What does smallest mean?
The smallest means the intersection. Like P of t, the interval of continuity for P of t is this one. The interval of continuity for Q of t is this. Now, tell me the interval where P of t and Q of t is continuous. Both. The smallest intersection. That is negative infinity to 0. Or negative infinity to 0 is contained in P of t and Q of t. Make sense? And that contains the initial value. So the initial value, interval of existence is negative infinity to 0. Is that clear? Are you all okay with that? All good? Okay. Now, let's pick a problem like this. T minus 3y prime plus natural log of t times y equals 2t and y of 1 equals 2. So the step 1 is obviously you're going to make a coefficient of y prime. Make the coefficient of y prime equals 1. So you're going to divide by t minus 3. So you are going to get y prime plus natural log of t divided by t minus 3 times y plus 2t divided by t minus 3. And my initial value is y of 1 equals 2. Do you agree? Now, what is my p of t? Can you identify the function p? Very good. Natural log of t over t minus 3. What is q of t? Obviously, very nice. So now, where is p of what is the interval of continuity for the function p? Where is the function p continuous? Say it loudly, please. 0 to 3 union 3 to infinity. Do you all agree with me on that? 0 to 3 union 3 to infinity. And where is the function q continuous? Negative infinity to 3 union 3 to infinity, right? Now, where is my initial value? Y of 1 equals 2. In which interval does y of 1 equals 2 belong to? Y of 1 equals 2 means when t is 1, y equals 2. So we are looking only at the t value, not the y value. Please remember that. So which interval does t equals 1 belong to?
0.
This one, right? Do you agree with me on that? So the interval of existence for this problem is 0 and 3. So I was not able to solve this problem. The only way is numerical method. So if you want to try, you can try, but I was not able to solve it. But I want to tell you that I know that I cannot solve this problem. However, if I'm trying to find a numerical solution, I'm going to find it only 0 to 3. Are you with me on that? Why? Because if my initial value was, let's say, if the problem was the same, which is y prime plus natural log of t divided by t minus 3 times y equals 2t divided by t minus 3. And let's say I'm just making it up. Don't question me on the accuracy of the problem. I'm just trying to have a little bit of width here. So if I have y of 4 equals 6, then my function p is natural log of t divided by t minus 3. My interval of continuity for function p is 0 to 3 union 3 to infinity. My function q is 2t divided by t minus 3. My interval of continuity for q of t is going to be negative infinity to 3 union 3 to infinity. This tells me that the initial value tells me that when t is 4, y equals 6. So my initial value t is present in that interval. So the interval of existence for me would be 3 and infinity. Do you see the difference? Do you see how I'm changing stuff? Is that a good illustration, right? So that's how you find the interval of existence for linear problem. Linear problem is pretty straight shot. Make the coefficient of y prime equals 1, find p of t, find q of t, find the smallest interval where p of t and q of t are continuous. Where does the initial value belong to? That is your interval of existence. Done. Is that clear? Yes.
Do you ever get a situation where they won't overlap over the common point?
No. All good? So there is a chance that you will see problems like this on the assessments, like quizzes and tests. Okay, but of course I did not say this on quiz 1, but eventually one of the possible questions would be that. Is that clear? Are you good? Now let's move on to the nonlinear problems. Do you think nonlinear problems will be this simpler? Obviously not, right? The question is pretty obvious. Now let's start with the nonlinear problem that we all know. The one y prime equals 3 minus 2t over y, and I think the problem was y of 1 equals negative 6, right? Y of 1 equals negative 6. Do you agree with me? That's a problem that we have. We attempted this problem long time ago, so I'm just picking the problem which is very familiar to us, so that we are in the similar familiar ecosystem kind of thing, right? So this is first order differential equation, right? Linear or nonlinear? Autonomous, non-autonomous? Non-autonomous, okay. Now, which method, variable separable or method of integrating factor? Variable separable, okay. Good. So you solved it already. We did it already, but let me do it again so that the more the merrier kind of thing. So you would write y dy is gonna be 3 minus 2t dt, right? So integrate both sides. So when you integrate both sides, you get integrate both sides with respect to t. So when you integrate both sides with respect to t, you get t squared plus c1, right? Then you want to use your initial value t equals 1, y equals negative 6. So that gives me what did that give me? 18 equals 3 minus 1, 2 plus c1. So c1 is 16. So we had a pretty good discussion on this problem. At that time, I think the problem was, can we distribute 2? Of course, yes. We got y squared is going to be 60 minus 2t squared plus 32. Do you agree with me on that? This is the solution of our first order nonlinear initial value problem in the implicit form using the variable separable method. I called it implicit because I was not able to isolate y by itself here, right? Then there were several questions. Can I apply the square root and do all that? Yes. And we saw how the sketches, like how the graphs used to be ellipses and all that. Do you remember all that? Just last week, right? All good? Okay, we did that, right? So then the next thing we did was, okay, let's say you apply the square root, then you get plus minus 60 minus 2t squared plus 32. Do you agree with me on that? So y value could be, and we also said, y cannot be 0. So that means y cannot be 0 means your solution is like ty axis. Y cannot be 0 means you're like, it cannot be the horizontal axis. So we said the solution has to be either above the horizontal axis or below the horizontal axis. Remember the discussion? Now, where is it going to be? Is it going to be above or below? Why? Right. So the initial value is when t is 1, y equals negative 6. So we want a solution that should be passing through y equals negative 6. So it has to be at the bottom. So, So it has to be at the bottom. I mean, this is a rough sketch. Again, don't hold me to the accurate scale. So that's how the solution might look like. Are you with me on that? So t equals 1, y equals -6. The y value has to be negative. So I'm going to pick -6t minus 2t squared plus 32. Do you agree with me on that? Are we all together so far? So what would I do on the, now there are two things running. One is the existence of linear problem is very straightforward. That's one thing. The second thing that is running is the nonlinear problem is much more complex. So which you are seeing much more, is more involved than the linear problem. That's what you're seeing. The other one you're seeing is, I'll come back to that later. Now the question is, when I said, I could have my solution above the horizontal axis or below the horizontal axis, but it's not on the end, it's only a certain portion below the horizontal axis. It's only this region is my region of the solution. Do you agree with me on that? My differential equation has a solution only in that particular region. Do you agree with me on that? So what are my t values? That's a question that we would have. So I want to find the interval of existence. So what is my, what are the t values between which my solution exists? Okay, so how am I going to work? I'm going to work with saying, okay, 6t minus 2t squared plus 32 is equal to 0. I'm going to set it to equal to 0. I mean, this is, now once I do that, it's pretty obvious for you. It's like, quadratic equation. So I'm going to use the quadratic formula. So factor it out, t squared minus 3t minus 16 equals 0. So, I mean, this implies t squared minus 3t minus 16 equals 0. So, obviously, using the quadratic formula, it goes 3 plus minus 9 plus 64 divided by 2. So, obviously, this gives me t is going to be 3 plus minus square root of 73 divided by 2. Is that clear? So this tells me that this t value is 3 minus square root of 73 divided by 2, and this t value is 3 plus square root of 73 divided by 2. So I'm telling that this problem, this nonlinear, non-autonomous initial value problem has a unique solution just in this interval, not everywhere. You see that? For these values of t, I have a unique solution. If I go beyond these t values, I will not have a unique solution. Is that clear? Make sense?
Why is it not inclusive of?
Because when I include them, what happens is the radical inside becomes 0, and then y becomes 0, but y cannot be 0 from here. Because if y is 0, then the differential equation doesn't exist. Right? Are we all good? Yes? When I was growing up, I was always thinking the existence theorem for nonlinear problem is really very analogous to real life. That means when you go to buy a home, they'll tell you, they'll show you a plot of 10,000 square feet. But then when they really build a house, they'll build you a house in maybe 1,500 square feet or 2,000 square feet. And they say the rest of them is yard. You cannot even touch it. Instead, you have to keep mowing the lawn and be a slave to that, but you cannot do anything on that. It's something like that. The interval of existence is something like that. It said y not equal to 0. You can graph the solution above the horizontal axis or below the horizontal axis. It's very tricky. It's appearing as if, the entire negative axis is your solution, but it's really not. Your solution really lies in a tiny interval between 3 minus square root of 73, in whatever that value is, in that tiny interval. Are you with me in that? Clear?
So, how do you write the internal of existence?
Just like this, Romal.
So, but when you say y is cannot equal 0, can you explain that first?
Y is not equal to 0 because the reason is if you, there are two ways I can explain that. Y prime equals 3 minus 2t divided by y, and I said y not equal to 0. If y equals 0, I mean, rewrite this differential equation like this. I mean, y times y prime is going to be 3 minus 2t, right? Now, if you say if y is 0, then you get 3 minus 2t equals 0. There is no differential equation to begin with. Do you see that?
Yeah.
So, what are we solving? Make sense? So,
Would that interval include 0? 3 minus...
yes, yes, t is 0. Remember that.
Alright.
These are the t values,
Yeah.
not the y values. Right? So what did I do? This part is the solving the first order nonlinear problem using variable separable, getting the explicit solution, but the interval existence is this tiny interval around the initial value. Right? Do you all agree with me on that? All clear? So this is a problem, kind of problem you will see in the assessments as well. Find the interval of existence. So you will find the solution using variable separable, then find the interval of existence. Now with this backdrop, let's look at the existence theory for the nonlinear problem. Okay, this theorem, I'm not even giving you mathematical justification because it takes a long time. I mean, easily at least one lecture. Many of your undergrad textbooks, there is only one undergrad textbook which gives you a rough sketch of mathematical justification. It's called Picard's existence theorem. One of the ways is Picard's existence theorem. It's a very important technique. You can demonstrate existence of the first order initial value problem using several techniques. One of them is Picard. So typically historians, what they do is the moment they see first order initial value problem, they run to Picard's and see, okay, can I prove the existence? It's Picard's existence theorem is obviously by the person Picard in somewhere in 18th century. And I forget, he is one of the teachers of Leibniz or Newton, one of them. He came before them, I think. If my memory is right. If I'm wrong, I'm wrong. I apologize for that, but that's what it is. Okay? Now, more important is, what does the theorem say? Let R be a rectangular region in the ty plane defined by where your t is between alpha and beta and your y is between gamma and delta. So this is the rectangle that they're talking about. Alpha is here, beta is here, gamma is here, delta is here. So you have a rectangular region. Okay, that's your domain. Okay? And then what does the theorem say? If the function is continuous and partial f partial y is continuous on the region, so that means if and this region contains the initial value, remember that the initial value is here. So if the function f is continuous and partial f partial y is continuous everywhere in this region, okay? Everywhere in this region, then the Picard's existence theorem tells you that there exists a unique solution in some smaller interval around the initial value. It doesn't tell you that you're guaranteed a unique solution in the entire rectangle. No, it tells you that there is a unique solution in some portion, in some smaller rectangle around the initial value. That's all the Picard's existence theorem is saying. Are you with me on that? So if the function is continuous and the partial of partial y is continuous on a bigger rectangle, then the existence theorem is saying that the solution exists and is unique. Unique means only one solution. There exists a solution and is unique on a smaller rectangle. That's what is depicted by the shaded lines. That means that's a smaller interval where you have a unique solution. Is that clear? Yes or no? All good? Okay, now how does this theorem apply to our problem? That's the next question that we have, right? Now y prime equals, this is like, this part is using the theorem, we got everything for the test and assessment. This is like, for the understanding. Y prime equals f of ty and y at t naught equals y naught. Now, if you pick the problem, y prime is equals 3 minus 2t divided by y, in y at 1, I think, is negative 6. Y of 1 is negative 6. So you have t naught equals 1, y naught equals negative 6, and my function ty is 3 minus 2t over y. Do you agree with me on that? Yes? Yes or no? And what is my partial f partial y? Now, if you have done 2551 multivariable calculus, it's pretty obvious for you. If not, this is nothing but the derivative of the function f with respect to y. So we are treating t as a constant. Treat t as a constant. I mean, very quickly. So this will give you what? I mean, if you differentiate it, you get negative 1 times 3 minus 2t times y to the negative 2. So that gives me 2t minus 3 divided by y squared. So again, this is my partial f partial y. Is that clear? Everyone okay? I'm trying to map it up with the map the problem that we did before with the existence theorem. So the function f is this. T naught is 1, y naught is negative 6, partial f partial y is this, right? Is that clear? Are we all good? So now you can see that, okay. Now you can see that the function f of ty, which is 3 minus 2t over y, is continuous everywhere except, except y equals 0. And your partial f partial y is nothing but 2t minus 3 divided by y squared is continuous everywhere except y equals 0 again, right? Are you with me on that? So that means, again, we are saying the solution is either above the horizontal axis or below the horizontal axis, but the initial value is below the horizontal axis. The solution should lie below the horizontal axis. And this theorem tells us that there is a smaller interval on which the solution exists, and that interval is really the interval of existence for us turned out to be 3 minus square root of 73 divided by 2 and 3 plus square root of 73 divided by 2. Is that clear? So that's how this problem is in compliance with the Picard's existence theorem. So once actually you know the interval of existence, you go about finding the solution, but here I demonstrated the other way around. I found the solution, the interval of existence, and I showed the compliance to you. Is that clear? Are we all together? Any questions? Okay. So that's what is demonstrated here anyway. Now let's look at the problem. Y prime equals y to the 1/3, y of 0 equals 0. Right? Do you agree with me on that? Now let's look at the problem from the computational perspective that we know. Right? This is a first order problem. Agreed? Yes? Autonomous? Right? Which method would you use to solve? Variable separable? Yes? Yes? Okay, so when you use variable separable, you get negative 1/3 dy is going to be dt, right? So you would integrate both sides. When you integrate both sides, you get y to the 2/3 divided by 2/3 equals t plus c1. Right? So that gives me 3/2 y to the 2/3 equals t plus c1. Now I use my initial value prescription, which is y of 0 is 0. So t is 0, y is 0. So when I do that, c1 is 0. So my solution is really 3/2 y to the 2/3 is going to be just a t. Agreed? Yes.
Why can't you use integrating factor for this problem?
Because it's not linear, but I will circle back to that question in a moment from now. Okay? Is this clear so far? So now, let me write this out. 3/2 y to the 2/3 equals t. So if I'm doing silly computation just to humor myself now. 2t over 3. So I want to isolate y. So that's going to be 2t over 3 to the 3/2. So that I get plus minus. Do you agree with me on that? Remember my solution, my differential initial value problem was in y of 0 equals 0. That is what is my differential equation. This is my solution. Is that clear? Do you agree with me on that? Yes or no? Yes. Now, can you look at this problem? So how many solutions did I get? 2? Okay. Can you look at the problem and tell me any more solutions? Wilson, are you here today? No? I only know the names from Piazza, and I don't know who you are. So I'm going to say names like the ones I know. Rihanna? No? You asked a question on Piazza, so I know your name better. Olivia? No? Okay. So what is the other solution? Do you know? Even if you're here, if you didn't say your name, I can't find out, right? You know. So what is it? Yes.
I guess from I was going to say from negative infinity to infinity.
I want a solution, which means I'm looking for a function. Yes.
The fact that it has a square root still attached to it, so it's plus or minus?
Yeah. No. One more. This tells me that I have two solutions. Okay. Plus 2t over 3 to the 3/2, and the other one is negative 2t over 3 to the 3/2. Right. I have two already. So I'm saying, are there any more that you can see from a problem? I mean, without really solving, just see and count. Yes. Fantastic. Y equals 0. If you put y equals 0, y prime is 0, so it satisfies the differential equation, it satisfies the initial value, so that's also a solution, right? So do we have any more? We don't know, right? I mean, we just y equals 0, thanks to her, we know it. But otherwise, we won't know. We cannot really come up with those things, right? Is that clear? So now, this is our solution. So what does our theorem tell us now? Let's look into, before I move on, I want to answer his question. See, y prime of t plus p of t times y equals q of t. Now in here you can see that there is this is how you write a linear first order ODE. Okay, first order ODE. In the linear first order ODE, the exponent of y is 1, but in the problem I have y prime equals y to the 1/3. The exponent of y is not 1, it is 1/3. Hence it is not linear, so I cannot use method of integrating factor, so I ended up using variable separable. Is that clear? Yes? Okay, so the next thing I want to talk about is, okay, now how does this, how are we going to analyze this problem with the Picard's existence theorem that we just talked about, okay? So in here, what is my function f of ty? It is going to be y equals 1/3, right? And did I do all that analysis? No, I did not do any analysis. So where is my function f continuous now? Oh, everywhere, right? Very good, everywhere. So all y. And all y, all t is continuous everywhere. Right? So that means everywhere means all t, all y, everywhere means what? It's the entire ty plane, entire 2D plane, right? Do you agree with me on that? So what is partial f, partial y? You're going to differentiate with respect to just y, there is no t. So it's just like a normal derivative. So 1/3 y to the negative 2/3. Let me just get rid of the computation so that you pay attention to the rest. So that is my partial f, partial y, right? Where is it continuous? Where is partial f, partial y continuous? Everywhere except 0, right? Is continuous everywhere except y equals 0. Do you agree with me on that? So what is our theorem telling? Our theorem is telling you have, let R be a rectangle, right? If your function f in partial of partial y is continuous everywhere in the rectangle containing the initial value, do you agree with me on that? Yes or no? So now I'm saying my initial value is 0, 0. This is my t-axis, this is y-axis. So no matter what rectangle I pick, do you think is my function f and partial y continuous everywhere inside the rectangle? No. Do you agree with me on that? Right? But why? Because right at the initial value it's not continuous, right? So can I apply this theorem? I can't even apply this theorem, right? The theorem cannot be applied here. The hypothesis is not satisfied. Theorem can be applied. The theorem cannot hold good here. So if it doesn't hold good, what does it mean? It means the theorem does not guarantee me a unique solution. Do you agree? Unique means what? Only one. The theorem does not guarantee me exactly one solution. Do you agree with me on that? So when it doesn't guarantee me exactly one solution, what is the theorem saying? I have no idea of your problem. I'm walking away from the problem. That's what the theorem is telling me. So I could end up getting 0 solution, multiple solutions, no solutions, all up in the air, right? But luckily, this problem was easy enough for me to attempt the variable separable method. And when I attempted the variable separable method, I got a multiple solutions. Do you agree with me on that? So you see how this theorem is consistent with the solutions of the problem. That's one way to look at it. Yeah.
What does it mean when both are continuous, f of t and y and partial derivative? Like,
You're asking what does it mean?
yeah, like if both of them are completely continuous everywhere.
Yes. What does it mean?
Yeah.
Is that what you're saying?
Yeah.
So you want to feel it? Is that what you mean? Okay. What does f is continuous means? Let's say, for example, now I'm hand waving a lot of details, okay, just to make you hopefully make some sense to you. I don't know if I'll be successful or not. So let's say if my solution was like this. Oh no, why do I do that? I don't need to do it because I have a solution actually. Okay, these are my solutions. I graphed it, right? Now what happens is, you see, when I say function f is continuous means what? That means I'm able to draw a curve without like very smooth where the function is differentiable. Now partial f partial y is not continuous means what? I cannot draw, that means the derivative does not exist, right? The derivative does not exist means, what does it mean? That means you can draw infinitely many tangent lines, or there is a sharp edge, or it becomes unbounded, or there is a break in the graph from our knowledge of calculus, right? So if you look at the solution, because there is a sharp edge, how many tangents can I draw there? I can draw infinitely many tangents, right? That's one interpretation you can think of it is that way. One possible interpretation. Don't
Yeah, well, in the sense of like the solution, what does the theorem mean? Like if you have, you said that it
the
doesn't
theorem is
work-
telling.
You said that it doesn't work if y is equals to 0, like because it's not continuous and y is equals to 0. So what if it was? Like what would that tell us?
Oh, you're saying here, I'm saying my, here is f of ty is continuous everywhere, but partial f partial y is not continuous at y equals 0. You're saying if it is continuous at 0, what would it look like? What would be the scenario like? It would be like the previous problem. Because you see, if in the previous problem, you had function is continuous, partial derivative is continuous, so you were guaranteed entire bottom half of the plane, but your solution ended up existing only in a certain interval. And that would end up to be a nice function, a continuous function. That's how it would turn out. Make sense? Are you all with me? This one is for fun and completion sake. There are certain things I need to, they handpicked certain topics in consultation with your major. So this is one of the things that came up. So I'm just completing it. I don't know where you will see it again, but at least if you see it again, you have seen it. Okay? Okay, now the next problem I have is that. So what are we talking about? We are talking about linear problem is pretty straightforward. Non-linear problem, if your function is continuous, if your partial derivative of f with respect to y is continuous, you're guaranteed a unique solution in some smaller interval around the initial value. We did another problem where, you know, your function f is continuous, but your partial f partial y is not continuous. Then in this case, what you got is there exists a solution because, I mean, if the function, very loosely speaking, if your function f of ty is continuous on a rectangle R containing the initial value y of t naught equals y naught, then there exists a solution in some interval. There exists a solution. We are not really telling that, okay, how many? Is it only one? Is it two? Is it three? Is it four? We're not specifying the number, but we are saying there exists a solution, but uniqueness is not guaranteed. Are you with me on that? That's another thing. The other one, this is a nice, sweet problem. It looks very nice. I mean, you know, but very tricky. Y prime equals y squared, y of 0 equals 1. What could go wrong, right? I mean, you know, when you look at it, what is the function f? Y squared is continuous. Partial of partial y is 2y is continuous everywhere. Do you agree with me on that? So you would want to think everything is hunky-dory, but let's look at it. So, you know, you want to use, I mean, you know, first, you know, this is a first order differential equation. This is non-linear because of y squared, right? So you would use variable separable method. You cannot use method of integrating factor. So you would write, okay, y to the negative 2 dy is going to be dt. So you want to integrate both sides. So that gives you negative 1 over y is going to be t plus c1. Then you're going to use initial value t equals 0, y equals 1, correct? Then what does that give you? It gives you negative 1 equals c. 1, then that gives you negative 1 over y is going to be t minus 1. So 1 over y is 1 minus t. This is very easy, so I'm just rushing it out. 1 over 1 minus t. Are you with me in that? And you know that from the solution t cannot be equal to 1. Why? Because if t equals 1, the solution becomes unbounded. Or you have a vertical asymptote at t equals 1. Clear? Very straightforward. No complexity at all. Probably one of the easiest variable separable methods, one of the easier problems that we have done so far. Right? All good? So now let's look at what does our theorem tell us. Okay? And the graph of the solution is here. I already did that. Okay? What does our theorem tell us? F of ty is going to be what? Y squared? Where is f continuous? Everywhere again? Are you with me? Yes? Okay, it's continuous everywhere. Okay? Where is partial f partial y continuous? What is partial f partial y? 2y is continuous everywhere as well. Right? So what does our theorem tell us? Our theorem tells us that there exists a smaller rectangle around the initial value where you have a unique solution. Do you remember that? Do you remember the picture? There exists a smaller rectangle, the dashed lines one, around the initial value where you have a unique solution. So what we are saying is that, in here, okay, the t equals 1, you have a vertical asymptote, y of 0 equals 1. So maybe your the smaller rectangle cannot go beyond 1 or cannot touch 1. Does it make sense? It has to be before that, before t equals 1. So your interval of existence from here is going to be negative infinity to 1 because your initial value t equals 0 belongs here. Make sense? You can draw, there exists a unique solution in a smaller rectangle around the initial value, but please remember that your rectangle cannot touch t equals 1 or cannot go beyond t equals 1 because you have an asymptote or a discontinuity of the solution there, right? So what are we saying? If so your solution might get affected by the continuity of f or continuity of partial f partial y or the continuity of the initial value or the continuity at the initial value or the solution itself. So when you come to the nonlinear problem, you have to pay close attention to what is the function f, what is partial f partial y, where is the initial value, what is the solution like. All those scenarios you have to pay attention to. But whereas linear problem, very straightforward. The smallest interval, which is in the intersection of P and Q, containing the initial value, is the interval of existence. Boom. Is that clear? That will be the difference between the study of linear first order initial value problems and the first order nonlinear initial value problems. Make sense? Clear? All good? So how would I ask on the test? If I'm asking you on the test or the quiz, I will ask you more a problem like this, like, this one, or more a problem like this one, find the interval of existence, so that you find variable separable, get the solution, find the interval of existence, give me the interval of existence, and be done with it. Okay? Like
Can you explain what difference you did in solving this one and the one that you just solved? Because in this one you like showed us what's the theorem like afterwards after solving it.
Right.
Whereas with the other one you started with.
No, the other ones also, I showed you how to solve it first, and I got multiple solutions, and I justified my multiple solutions with the theorem by saying here partial f partial y is not continuous in the rectangle containing the initial value, so the theorem cannot be applied. So, but because the function f is continuous, there is a solution, not a unique solution.
No, not that one. I'm talking about number 76. The one you just
Okay, here what I'm saying is, okay, I have my function f is continuous, partial f partial y is continuous. So, there exists a smaller rectangle around the initial value where there is a unique solution. But now what I'm saying is my smaller rectangle cannot touch t equals 1 or cannot go to the right side of t equals 1. It has to be to the left of t equals 1. So the interval of existence is 0 and negative infinity to 1.
I'm confused.
Okay, I'll repeat. This is my initial value, right? Y of 0 is 1. So what I'm saying is my rectangle can be, it has to be to the left of t equals 1. It cannot touch t equals 1 because if it touches t equals 1, my solution becomes undefined. So my smaller rectangle where there is a unique solution has to be to the left of t equals 1.
Okay, and you find that out by like since the denominator cannot equal 0, that's why it's t equals 1.
Correct. The denominator tells me t cannot be equal to 1, but my initial value tells me that it has to be to the left of t equals 1.
Okay.
Make sense? All good? Clear? No questions? You have a question? Yes.
Yeah, so just is not continuous, then this theorem is not valid.
Then if, okay, that's a hypothetical scenario. If partial f partial y was not continuous in this, right, is not continuous on a rectangle in which includes the initial value, then the theorem cannot be applied. So in this case, you see, I mean, I didn't ask this question, but you can see, okay, one of the solutions is y equals, what is that? One of the solutions is, then in that case, how do I put it? Then the theorem cannot be applied, so there cannot be a unique solution. There can be more than one solution in this problem. And I don't know what the other solutions are, but one of the solution is this. Is this clear?
Yeah.
Yes.
So if the theorem doesn't apply, is that saying for sure there's not a unique solution, or you just can't tell?
I can. I don't know. I'm
So
at
there
that
could
point.
be- There could be one.
There could be no solution. There could be multiple. I don't know. I cannot guarantee a unique solution. That's all I can tell you.
Okay, but it could be a unique solution.
Oh, you're asking, could there be a unique solution?
Yes.
Possible.
It is.
Yes. Okay? All good? Okay, that finishes this section. So now I'm going to go back to the previous section. In the previous section, I was doing applications and I did not do one application, which was a money problem or the interest rate problem. That was the only one I didn't do. Rest of the ones I did. I didn't want to start out with this problem because I didn't know how the lecture with the existence theory would go. So I wanted to get that covered first so that I can come back to application. So here is the one. The last application for you from this thing. So this, there are three scenarios that I want to think about. Case one. Case one is, let's say, case one is, let's say you're born and somebody invested P dollars in your name in some account and it's growing, the interest is getting accumulated. Are you with me on that? So when the interest is getting accumulated, it's like when you invest some money in the first place, it's like the initial volume of the tank is some specified amount and the initial concentration is something, and it's growing. That means that because of the interest rate, which means there is a constant inflow of money. And then let's say you are also contributing some K dollars per year every year. Okay, you're not really taking out any money, you're just constantly contributing. So there is a tank where there are two inputs, no output. So you will obviously you will anticipate at some point of time the tank will overflow, right? The case number two is, let's say you have P dollars in your account and there is a growing interest. I mean, the interest is being accumulated, so the money is flowing in, but you're also withdrawing some dollars, like, for expenses. So there is some inflow and there is some outflow. Are you with me on that? So if the interest is bigger than the expenses, then you will end up saving more money or the money will overflow at some point of time. But if the interest is lower and expenses are higher, inflation is higher, then the outflow is more and then tank will get empty, which means the account will get to zero very fast. Are you with me on that? Then the third scenario is, okay, there are, you borrowed some money. Okay, you want to build a house, maybe you want to buy a car, maybe, I don't know what are the things you want to buy, but maybe a car or a house, popular ones. So you with me on that? So the loan is increasing, but then when you pay the money, the loan is decreasing, so there is an inflow and outflow. So if you pay faster than the accumulation of interest, then you will pay off the loan very fast. If your monthly payments are less, then the interest will increase in quantity, and then you will not be able to pay off. The loan will become infinity. Is that clear? Yes.
Is there a computational difference between case 2 and case 3?
Yes. No, is there a difference? No. No. Okay. But in both the cases, when you're withdrawing, it will be negative. So how would it be? It would be, I mean, you were talking about your future value is going to be whatever is the present value, right? Plus, plus the interest accumulated, right? Plus the yearly contribution. Let's just say yearly contribution. So in the case of if you're paying off the loan, the monthly payments or the yearly payments. Are you with me on that? If you're adding the money to your 401k account, then it is a yearly contribution. Are you with me? So the future value is nothing but P of t plus delta t. The present value is P of t. The interest is a simple interest, Rp delta t. Yearly contribution is K times delta t, right? Now, if your year is 1 year, delta t is 1. If you're telling your contributions, if your change in time is quarter, then delta t is 1 over 4. If the change in time is month, then it is 1 over 12. If it is weeks, it's 1 over 52, right? It's pretty standard. So what would you do? You would want to compute the change in t. So you would write P of t plus delta t minus P of t equals Rp delta t plus K delta t. Okay, then that is nothing but delta P equals Rp delta T plus K delta T, right? So divide by delta T and let delta T go to 0 because you all studied calculus. That's the next thing that you want to do. You would get something like dP dt equals Rp plus K, right? Rp plus K. Like it's very consistent with your tank problem. dP dt is the change of amount with respect to time in your account. Rp is the interest accumulated. K is your yearly contribution. K is positive if you're adding to the account. If you're withdrawing or if you're paying off the loan, K is negative. Is that clear? Are you all okay with that? So now, and of course, your initial value is P of 0 equals P naught. Okay, that's the initial concentration of salt or initial amount in your account and so on and so forth. Make sense? Okay. Okay, now, so if I have a problem, I can write this way. Do you agree with me on that? So what method can I use to find the solution? Method of integrating factor or variable separable or both? I can use both, but variable separable works fine. So do you think, can I safely assume that you will carry it out and do it on your own at your free time? Is that okay to say that? Yes. Yes, thank you. So then my solution would be something like P naught e to the RT plus K over R e to the RT minus K over R. I hope I'm right, because I want to get hopefully the cooler part or what I think is the appealing part of the problem, not the complication, right? So if you're not making any contribution, that means let's say my K is 0, then my P of t is P naught e to the RT. That is like the compounding interest formula. Do you see that? It's pretty consistent with that. So that's how I remember it. That's a special case, right? Now let's look at the problem. Okay. Now let's say this is okay. A student has taken a loan of $20,000. So that means you're starting off P of 0 equals 20,000. Okay. And the interest rate, if the interest paid on the principal is continuously compounded at 8%, so R is 8%, so which is 0.08, right? And you're making an annual payment of $487 per month, so that's going to be 487 times 12, and I evaluated that already, so that's going to be $5,844 per year. Do you agree with me on that? Yes or no? So can I model such a scenario? How is my loan amount changing with respect to time? That's the question that I have. Okay, so how can I use my first, now that I studied my differential equation, okay, besides circuits, besides tank problems, population dynamics, and Newton's law of cooling, will it predict my student loan as well? Okay, yeah, the differential equation is interest accumulated plus the payments made, R times P minus K. So R is going to be 0.08. P is the variable P itself, K is negative 5844. You're paying off your loan, so that means you hope that the loan will go to zero at some point of time. Whenever you're paying off the loan, the sign is negative. Are you with me on that? So that's what it is. And your initial value is P of 0 is 20,000. Okay? Are we all together? And now, this is what is interesting to me. I hope you find it interesting as well. Now I will run through the qualitative analysis or the critical point semi-stable, stable, asymptotically stable now, just like how I ran with it in the electric circuit problem. Are you with me on that? Okay, now let's say dp dt equals 0.08p minus $20,000, right? Is that clear? And my P of 0 is not 20,000, sorry, it's 5844. And my P of 0 is 20,000, correct? Now, what is my critical point? How do I find my critical point? 0, right? Very good. So that gives me 0.08p minus 5844 equals 0. Do you agree? So this means, okay, I'm going to isolate my P, and because I just did the computation in my previous lecture, I have it right on my calculator, and that gives me that much. Okay, so my critical point is that much. Are you with me on that? Yes? So now what am I going to do? I'm going to draw a phase line. So what does my phase line say? I want to pick a number less than 73,050. What number do you want to pick? What number do you want to pick? 0. Very good. So P is 0. So my dp dt is going to be what? Negative. Do you agree with me on that? Then if I pick a number bigger than 73050, what number do I pick? Okay, 100,000. Okay, in my previous class I picked 80,000. Okay, in that case dp dt would be what? 8,000 minus 5844. That's positive. So my phase line would be, here is my critical point 73050, and for the values less than the critical point, my solution is decreasing. For the values bigger than the critical point, my solution is increasing. So what is the stability? What is your comment? Classification of stability of critical point?
Unstable.
Very good. So P equals 73050 is unstable. Okay, now I'm just replicating the study that I did in my very first class, the section 1.2, right? Do you see that? If I didn't tell you the context of the problem, you would be okay with saying that it's a nice, easy problem. So now I want to get the sample solution curve. That's my next thing to go for. Sample solution curve, okay? So if I want to go for sample solution curve, this is my critical value, P equals 73050. Remember my dp dt is going to be 0.08p minus 5844. So my second derivative is going to be 0.08p prime. So in here the first derivative is positive and the second derivative is also positive. So it's increasing and concave up. For the values of p less than the critical point, my solution is decreasing. But my second derivative is decreasing as well. So it's decreasing in concave down. So my sample solution curve is like that, right? Do you agree with me on that? So what does it tell you in the context of the problem?
Way too much time, we're gonna be paying a lot of money.
Say that again.
Way too much time, we're gonna be paying a lot of money.
No, something else. That answer is yes, but not with the sample solution curve. What does the sample how if you were to sell it to a person, how would you sell it? Like how would you interpret the problem? Yes.
If you owe less than 73 grand, you're gonna end up paying after some point of time, but if you owe more than that, you'll never pay it off.
Fantastic. Do you see that? So did Greece do? Okay, did one country went bankrupt in 2016 and that created recession in Europe and consequently all across the globe. Now, did the country do this kind of analysis, or was it this simple or this difficult? So you can, this student loan problem can be extended to studying the economies, because every country takes loans at a certain interest rate and they make certain interest payments. So the initial loan is this much, interest payments are this much, and monthly payments are this much, monthly contributions are this much. So will the country ever be able to pay off the loan or not? Can be decided just by the first section in our differential equations course. Now, so this tells you that, one last slide. So this tells you, okay, if you borrow $20,000, of course you would be able to pay off in approximately 4 years. If you borrow $40,000, you would be able to pay off in 10 years. So if your initial loan amount is different, then you will be able to pay off. As he rightly pointed out, if the initial loan is greater than 73.50, then there is no way. If the interest rates are fixed, like you're not refinancing it and you're not changing your monthly contributions, then you will never be able to pay off your loan. So that's how you decide it. Is that clear? Hopefully that's one other application of first order differential equations. So that pretty much brings the first order differential equations to a close. When we return on Tuesday, we will start with the higher order differential equations. Okay? If you have no questions, you can.